Thank you all so much for joining us for today's Lunch and Learn on climate science. I am so excited to be joined by my former professor, Karl Kreutz of the School of Earth and Climate Sciences at UMaine and the Climate Change Institute. My name is Abby Bradford. I am the Outreach Manager for Maine Conservation Voters and Maine Conservation Alliance. My role is to help Mainers from across the state make our voices heard in our political process, that we can protect our common home and our future. Maine Conservation Voters' mission is to protect and conserve Maine's environment. We help elect pro-environmental leaders to office, we help pass pro-environmental legislation, and we hold our leaders accountable without regard to political party. A few technical notes for today's event. You are all muted, but we do want to hear from you. Please send your questions and comments to me if you're able, or to all panelists if that's the option you have. I'll keep track of your questions throughout, and then I will ask Karl when we get to the Q&A at the end. Also, please note that this event is being recorded. We will share the recording with you all later this afternoon. Our agenda for today is first we'll be hearing from Karl, what you're all here for, get an introduction to climate science. After that, I'll do a quick call to action to let you know how you can take action on climate change. Then we'll do a Q&A and wrap up and announce next week's Lunch and Learn. All right, with that, I'll hand it over to you, Karl.
Whoops.
Yeah, let me know if you need help with the screen share.
It says my screen sharing has been disabled. Is that...
Ah, dear, here we go. All right, you are a co-host now. You should be able to share.
Okay, there we go.
Also, for those of you that have been joining our Lunch and Learns every week, you may notice that things look different this week. Normally, we are in Zoom meeting. We're trying out webinar this week, but we're finding some kinks. So we'll probably be going back to meeting in the future. But thanks for bearing with us as we try new technology. All right, Karl, take it away.
It works at all. Fantastic. Well, thanks, Abby, for reconnecting, and it's fantastic to be here today. Thanks for inviting me. Abby asked me if, well, she titled it Introduction to Climate Science, which is fine. I guess I would say my goal today is to give you sort of the big picture of climate science. By picture, I mean what have we learned about the climate system in general, but in particular, what do we learn from looking at past changes in climate, past changes in the carbon cycle that really inform where we are today and where the system may go in the future. So as an overview, and I should also note, just an aside, this fantastic artwork that Abby showed and that I have here on my introductory figure is from one of our former students, Jill Pelto, a fantastic artist. So I'd encourage you to look her up and check out her climate-related artwork. So this is what I'm going to cover today. Just give you a brief introduction to the greenhouse effect. That really is in many ways, the starting point from which we understand the climate system, where it's been in the past and where we are today. Anytime you're talking about the greenhouse effect, of course, the next thing you start talking about are greenhouse gases. So greenhouse gases in the atmosphere, and how they affect the well, what we call to the planet, but really how they affect the global temperature distribution and how that changes with time. And again, what I want to do here today is show you some things that we've learned by looking at past changes in climate that really inform how we think the system works and where it may go in the future. And then I'll wrap up by giving you a sense of some global scale impacts that we see occurring now, and particularly focus on ones that have direct relevance to us in Maine. Of course, there are a lot of local and regional scale climate effects that are happening here in Maine, and there are certainly many people here in Maine who are studying those in great detail. And I think Abby's going to follow up with some more lunches with those folks in the future. My job today, though, is to share with you things we've learned about the global scale system and those type of impacts that that then have relevance to us in Maine. So those are my 3 points today. So let's start with the greenhouse effect. Again, this is where we sort of think of the basic fundamental aspects of the climate system really boil down to this fundamental process. And that is essentially that most of the energy that we have available to us here on the Earth's surface comes from the sun. And that's solar energy strikes the Earth's surface because the Earth is, well, it re-radiates that energy back, tries to re-radiate it back out into space. So you see the orange lines coming in, that's solar energy, and then some of the orange lines go back out to space. So that's a normal function of any planet in our solar system. But for those planets that have an atmosphere, like of course our Earth, and for those planets that have an atmosphere with greenhouse gases in that atmosphere, the role of greenhouse gases is to take some of that energy that would normally go back out to space and redirect it back to the surface of the planet. So the simple way we think about this is that if the Earth in fact had no atmosphere, the temperature of the Earth's surface would be about 0 degrees Fahrenheit. In other words, all the water on Earth's surface would be frozen. But in fact, of course, the surface temperature of the Earth on average is about 60 degrees Fahrenheit. And it is that way because of the greenhouse gas concentrations in the atmosphere. The fact that we have an atmosphere with greenhouse gases keeps some of the solar energy at the surface and raises the temperature of the planet above where it would be without those greenhouse gases. So obviously that's an important and fundamental aspect of the climate system and the Earth system, is that we do have greenhouse gases that make the surface not only a place where we can have liquid water present, but also life present. So those greenhouse gases, in fact, really, really important to us. Conversely, though, what's happening now is that as we continue to put more greenhouse gases into the atmosphere, that blanket, if you will, or the blanket that surrounds the planet that keeps us warm, that blanket is getting thicker. So more of the energy that would normally go back out to back out to space is being trapped at the surface. And so that is in effect the greenhouse. That is the greenhouse effect, the trapping and re-radiation of that solar energy back to the surface. So greenhouse gases, though, I mean, this is the fundamental component in this process. And of course, we know that we are altering the greenhouse gas composition of the atmosphere significantly. Why is that? Well, simply put, it's because we put a lot of carbon into the atmosphere, and we've been doing that for some time. So this graph is simply an estimate of the amount of fossil fuels that have been burned through time and the carbon dioxide emissions that have come from those fossil fuels. So you can see back around the mid 1800s, say 1850, is when we really started putting greenhouse gases, burning fossil fuels and putting carbon dioxide into the atmosphere. And since then, that amount of the CO2 that we've been putting into the atmosphere has been going up. So today, we put roughly, as a global society, around 10 gigatons of carbon per year into the atmosphere. Now the units are sometimes hard to get your head wrapped around, but 10 gigatons, 10 billion tons of carbon going into the atmosphere every year is quite a bit. And if you were to estimate all of it, if you take this curve and estimate the total amount of carbon that we've put into the atmosphere since we started burning fossil fuels, you see that it's about 500 gigatons of carbon that we have as a society put up into the atmosphere over the course of the past 150 years or so. So that's carbon emissions. What has actually happened to the carbon dioxide concentration in the atmosphere? So this is it's a very famous graph in the climate science, well, in the climate sciences. This is known as the Keeling curve. It's called that because the scientist Charles Keeling, back in 1958, he was working at the Scripps Institution of Oceanography, and he started measuring carbon dioxide concentrations in the atmosphere. So this was the first time that someone was able to make accurate carbon dioxide concentrations in the atmosphere. And since keeling started in 1958. They've been taking routine measurements month after month, year after year. And what has become clear is that the carbon dioxide concentration in the atmosphere, which is over here on the left-hand side, you see the axis there. The unit is in parts per million. The important thing to note, though, is that today, the concentration of carbon dioxide in the atmosphere is over 400 parts per million. So I'm gonna ask you to keep that number in mind, 400 parts per million, because I'm gonna refer back to it a number of times as we look at the history of carbon dioxide in the atmosphere. So this is, as I said, this is a famous graph in the climate sciences community because it actually, there's so much information contained in here. One is that there's an obvious trend in carbon dioxide concentrations in the atmosphere over the past 60 years. You can see how we started around 320 parts per million in 1958, and now we're above 400 parts per million. Another interesting thing you can see in the red line, which are the monthly carbon dioxide values, is that it looks like a sawtooth going up and down year after year. And what that represents is the change in vegetation in the Northern Hemisphere through the course of the year. So right now, in June, in the Northern Hemisphere, we all have watched over the past month as the trees have greened and the vegetation has greened. Well, of course, what's happening is that all that vegetation is undertaking photosynthesis, which is pulling carbon dioxide out of the atmosphere. So in the Northern Hemisphere, in the summer, Northern Hemisphere summer, that's every time that sawtooth goes down, that's the Northern Hemisphere summer. And in the Northern Hemisphere winter, when all that vegetation gives its carbon back up to the atmosphere, you see the CO2 concentration go back up. So that sawtooth pattern that you see there, that's essentially the breathing, if you will, of the Northern Hemisphere. Vegetation growing in the summer and then dying off in the wintertime. So carbon dioxide in the atmosphere, of course, has a large role to play in just the natural vegetation and the natural biosphere. But this trend that we see with time is definitely due to human impacts and the burning of fossil fuels. There are ways that we as scientists use different types of chemical analyses to prove that that's true, and I won't take the time to go into that here, but I'll ask you to trust me that we know how and why this carbon dioxide is going up like it is. What's the effect of that? Well, as carbon dioxide concentrations have grown in the atmosphere over the past 60 years, those increases in greenhouse gases have been mirrored by an increase in the global average surface temperature of the Earth. So if you think back to that first figure I showed, where greenhouse gases are essentially a blanket sitting on the Earth's surface, what we've been doing by adding carbon dioxide and other greenhouse gases to the atmosphere has been to increase the thickness of that blanket. And so what has happened is that the temperature, the global average surface temperature, has gone up in step with those carbon dioxide concentrations. So these temperature data start back in around the late 1800s and go up until today, and you can see clearly the trend towards warming temperatures. And globally speaking, over the past 100 years or so, the global average temperature has gone up by about 1 degree Celsius as those carbon dioxide concentrations have increased. So you can ask many questions about this system, about how it works. And one way to get a better perspective on this relationship between greenhouse gases and the Earth's temperature is to look into the past. Because, of course, the Earth has been around for 4.5 billion years. The fact that we have data here for only about the past 100 years, well, 100 years is a pretty small snapshot in time when you're talking about a system that has been operating for over 4 billion years. So one of our goals as scientists, as a scientific community, is to say, what did the relationship between carbon dioxide and temperature look like at other times in Earth's history? And is there something that we can learn from that? There's lots of different ways to do this, to look at Earth's climate history. One of the ways that we specialize in at the University of Maine, and we have a big program doing this is that we collect ice cores, so cylinders of ice from the polar ice sheets of Antarctica and Greenland. And we also do this in many different alpine glaciers around the world. And it turns out that ice is a really valuable archive of past climate information. One of the reasons for this is because greenhouse gases actually get trapped in the bubbles that are in the ice, in these ice cores. So you can see the pictures on the bottom, these big multi-institution projects that we participate in down in Antarctica. We drill ice cores that go all the way down to the base of the Antarctic ice sheet, and that's on the order of 3 or so miles of ice. And so you can see one of the ice cores on the right-hand side there. If I were able to zoom in and show you the detail of that ice, you would see all the individual bubbles of air that are trapped in that ice. So when we drill an ice core, we know from different techniques that the ice is, let's say, 700,000 years old. It turns out that the gas in those bubbles is also 700,000 years old. So this technique of drilling ice cores has allowed us to reconstruct not only the greenhouse gas concentration in the atmosphere through time, but also temperatures with time as well. So what do those data look like? Here are some results from some of these Antarctic ice cores. So what we're looking at here is a graph of carbon dioxide concentrations. Now, again, we take the bubbles out of the ice, we extract the gases from those bubbles, and we make these carbon dioxide measurements. So with this technique, again, we can go back in time and tell you what the carbon dioxide concentration of the atmosphere has been in different times in the Earth's history. What I'm showing you here on the right-hand side of this graph is the year, it's around the year 1950. And on the left-hand side of the graph is around the year 1000. So this is roughly a record of carbon dioxide concentrations in the atmosphere over the past 1000 years. What do we see? Well, again, just like in the global temperature data that we looked at and the carbon emissions data, we see that in the early to mid 1800s, when we as a global society first started to really use fossil fuels and put carbon into the atmosphere, that's when the carbon dioxide concentration in the atmosphere really started to increase. So before the 1800s, you can see that the carbon dioxide concentration in the atmosphere was around, let's say, 280 parts per million. Remember that today, today's measurements in the atmosphere, CO2 concentrations are over 400 million parts per million. So we as a society over the past 150 years have increased the CO2 concentration in the atmosphere by about, well, over 100 parts per million. So I'm going to ask you to keep that number in mind too, because it's going to be relevant when we look even farther back in time. But this is a snapshot of the last 1,000 years. CO2 has been relatively constant, and then all of a sudden, when we started burning fossil fuels, you see the CO2 concentration in the atmosphere really start to increase. What about temperature? Well, here are estimates of the global surface temperature. Again, on the right-hand side of this graph is roughly today, around the year 2000. On the left-hand side of the graph is essentially the year 0. So this is about 2,000 years of temperature record, global average temperature record. And you can see a lot of interesting things here. Back around the year 1000 and prior to that, the Earth was actually relatively warm. It was a time period called the medieval warm period. We then went into a period, you can see how the temperature starts to decrease until it bottoms out in the year 1600, the year around 1700. That's a time period known as the Little Ice Age. But then in the mid 1800s, temperatures start to increase again. So in other words, these global average temperatures mirror the change in carbon dioxide concentrations in the atmosphere. So they seem to, at least at this scale, they see temperature and CO2 seems to go hand in hand. This figure, like with that Keeling curve, which is again, as I said, is a sort of an iconic figure in the climate science community. So is this one. This is known as the hockey stick curve of global average temperature because, well, in essence, it looks like a hockey stick with a long shaft and then the blade of the hockey stick coming into the 20th century as temperatures really started to increase. So that's a snapshot of the past 2,000 years. What if we go back further in time? And when I say back further in time, I'm talking about what we think of as the last great global warming. And by that, I mean the Earth was in an ice age about 20,000 years ago and rapidly came out of that ice age between about 20,000 years ago and 10,000 years ago. Prior to 20,000 years ago, here in Maine, we actually had an ice sheet sitting here in Maine that was as thick as essentially the Antarctic ice sheet is today. And that was an ice sheet called the Laurentide ice sheet. It covered a large part of northern North America. So on this graph, on the left-hand side is about 19,000 years ago. On the right-hand side is 9,000 years ago. And it represents the data that come from this big transition. When the Earth warmed, the Laurentide, the big ice sheet that was here in North America, disappeared. And in fact, this time period is a time when the ice sheet was retreating through Maine. So much of our landscape here in Maine is a function of this ice sheet that was in Maine and retreated through Maine during this time period. So notice what I want you to see here is that in red is the carbon dioxide concentrations from ice cores. Notice that around 20,000 years ago, we started at about 200 parts per million. Through this big global warming, we went up to about 280 parts per million. So carbon dioxide concentrations went up by about 80 parts per million, and the Earth lost many of its major ice sheets. The only ones that remain, of course, are Antarctica and Greenland. So that gives you some perspective. An ice age ended with an increase in carbon dioxide of about 80 parts per million. And remember that since 1850 until today, we've increased the carbon dioxide concentration in the atmosphere by over 100 parts per million. So a greater increase than what we see here during the last great global warming. The timescales are different. This, of course, occurred over several thousand years. But the magnitude of the change is something that we want to keep in mind because we are very rapidly changing the greenhouse gas concentrations in the atmosphere that are comparable to what we see during the last great global warming. Now for some even longer term perspective, these again are data that come from those same Antarctic ice cores. These are, this now is the longest current data set that we have from Antarctica. It goes from today back about 800,000 years. On the top of the graph in the blue, that blue line is again the carbon dioxide concentration in the atmosphere, which we've been able to reconstruct by taking the gas out of all those bubbles that are in the ice and meticulously putting those data together so that we have a continuous record of carbon dioxide concentration through time. On the bottom in the red is an estimate of temperature. I won't go into the details of how we do that, but suffice it to say that it's done lots of different ways, and we're confident that we understand the temperature record. So you can match those two up, temperature and carbon dioxide. And I think you'll be able to see that what this data shows over the past 800,000 years is that every time carbon dioxide concentrations in the atmosphere have gone up, so has temperature. And every time CO2 concentrations have gone down, so has temperature. And it turns out that on this time scale, every time carbon dioxide has gone down to notice about 200 parts per million, the Earth has been in an ice age. And every time carbon dioxide concentrations have gone up to around 280 or 300 parts per million, the Earth has come out of an ice age. And into a period such that we've known for the last 10,000 years or so. But for perspective, again, that's what these data, one of the things these data are very good at is showing you the perspective of where we are today. And where we are today, again, is over 400 parts per million in carbon dioxide concentration in the atmosphere. So if you were to take these data and extrapolate them forward, it's not that big of a leap to see how temperatures will be rising, are rising, and will continue to rise as we keep increasing those greenhouse gases in the atmosphere, thickening that blanket, and raising temperatures. So that gives you a sense of the perspective that we can gain by looking at the long-term record. What about impacts? Well, one of the, again, because we're down in Antarctica often, and we're up in Greenland often, one of the things that we also are keenly aware of is the fact that as we continue to increase greenhouse gases in the atmosphere, which then raise the temperature because of the greenhouse effect. Certainly one of the impacts is that we are losing ice on the planet. When I say losing ice, I mean we're losing ice from melting of the Greenland ice sheet. We are losing ice from the Antarctic ice sheet. And we're losing ice because of the melting of mountain glaciers around the world. What's the consequence of that? Well, that water that's melting is going into the ocean and of course raising sea level. So of the many climate impacts that we're facing right now, sea level rise is arguably one of the most fundamental impacts of increasing atmospheric temperatures is the melting of ice. And again, as I say, we spend a lot of time as scientists in Greenland, in the Arctic, and I can assure you that the Arctic is melting quite rapidly. I also say in this slide thawing because another impact on a global scale, particularly in the Arctic, is the thawing of permafrost. And so both of these are acting together. We're losing ice from the Greenland ice sheet through melting. So on the right-hand side there, you see a map of Greenland, and all those different circles represent the change in the amount of ice that's present in that location. Any place where you see a red circle, that means that ice is being lost. And anywhere you see a blue circle, that means the ice is growing. So I think you'll probably be able to see that by and large, the Greenland ice sheet is melting. Most of those circles are red, and the size of the circle corresponds to the amount of melting that's occurring. So we are watching this situation very carefully. Lots of scientists are studying Greenland and monitoring the amount of melting that's going on up there. Because again, when the Greenland ice sheet melts, that water, of course, goes into the ocean, which is having a direct impact on sea level rise. It's also having an impact that's relevant to us in Maine. The melting of the Greenland ice sheet is having an impact probably on ocean circulation, because you're putting, as the ice melts, you're putting a lot of fresh water into the ocean. And of course, fresh water is lighter and less dense than ocean water, so it sits at the surface, and that can alter the ocean circulation in the North Atlantic. So all of these effects together, these impacts, are things we're watching and studying very carefully. On the left-hand side, you see another climate impact in the Arctic. I'm sure many people have heard that the Arctic is losing sea ice quite rapidly. So these are actually satellite data starting in 1980 and continuing up until today. And you can see that the Arctic is losing its sea ice cover quite rapidly. So this is another sort of global scale climate impact from global warming that we're watching very carefully. And it turns out that the loss of Arctic sea ice is certainly not just an Arctic issue. Not only does that have important implications for shipping, resource extraction, and other impacts in the Arctic, but it also impacts us here in Maine and the mid-latitudes, because the loss of Arctic sea ice tends to change the way that the atmospheric circulation works. So weather patterns are reacting to this loss of Arctic sea ice. So this is another impact that we watch and study as carefully as we can. So again, relative to sea level rise, the Earth as a whole is losing ice. So it's not just Greenland, it's not just Arctic sea ice, it's mountain glaciers around the world are reacting to the increase in global temperature that we're seeing. So again, this is a figure that's showing the different circles are related to the amount of ice that's being lost. So anytime you see a color that's yellow or orange or red, it means that ice is being lost from that particular mountain glacier system. And you can see that around the world, they're all red and orange. There's only one that's blue, and that happens to be in the mountain range in Asia called the Karakoram Mountains. And folks are studying that quite carefully, have a good sense of why actually ice is being added to that particular glacier system. But in general, around the world, ice is being lost from mountain glacier systems. Like with Greenland, as that melting progresses, all that water is going into the ocean and raising sea level. So if you look at sea level data over the past couple hundred years, again, you see a common trend. As carbon dioxide concentrations in the atmosphere go up, which are part of the greenhouse effect, atmospheric temperatures go up. As atmospheric temperatures go up, that is melting the Earth's ice cover. That melting puts water into the ocean and raises sea level. So here are sea level data, and you can see over the past, again, since the sort of mid 1800s, sea levels have started to increase. And by now, between 1850 and roughly today, sea levels have gone up by on the order of 30 centimeters. So the scale on the left-hand side there is in meters. You see also projections of sea level rise for the 21st century. The reason why there's different colors are based on different carbon emission scenarios that may or may not play out as we move forward through the 21st century. So there's a fair bit of uncertainty in there based on the choices that we make about our carbon emissions. But sea levels, as temperatures rise, sea levels will continue to track those temperatures. There's no question about that. So that certainly has a direct and relevant impact on us in Maine. These are pictures from the Unit of Concerned Scientists from Vinalhaven, Maine, certainly during periods of flooding in the town there. And this situation, of course, plays itself out up and down the coast of Maine, a serious concern. Also, periods of chronic flooding. So chronic flooding defined as being greater than 6 periods of flooding throughout the year. That is increasing on the coast of Maine. Certainly, there are folks studying this in great detail, and I'd encourage you to talk to those folks. But what I can say from the global picture is that we studied this in the past, we study it in the present, we look at this on a global scale, ice on a global scale, and these impacts certainly are going to continue, and we need to be aware of how the choices we make now and in the future are gonna play themselves out. So I'll leave you with a couple takeaways before we get to the question and answer session. And again, I'm looking at this from the global scale, not only the global scale today, but the global scale over the course of Earth's history. And it certainly is true that greenhouse gases do in fact control what we think of as the Earth's thermostat. Um, the record of climate change over Earth's history is very clear, where we are able to measure greenhouse gas concentrations and temperature. We see that they go hand in hand. So the greenhouse effect and greenhouse gases do in fact provide a powerful thermostat on Earth's temperature. We also can see that the response of the Earth system to those increasing temperatures, again, I gave you an example of loss of ice, so melting of ice, melting of Greenland and other mountain glaciers. That response has obviously global significance, but direct significance to us in Maine. Sea level is of course a massive concern of ours in coastal Maine, so we need to always keep these global scale processes in mind when we're thinking about local and regional scale impacts. It is one big system, and so whenever I'm teaching my classes or giving talks, I encourage people to think the old adage, think globally, act locally, but it really is a global system, and the choices that we make with respect to how we particularly use carbon and impact the carbon dioxide concentrations in the atmosphere do have global impacts, which then come back to us. So we need to think about things as a system and how the system reacts as a whole. So I'll stop there. I know Abby has time for question and answer session, but if folks have other questions that we don't get to today or want to talk about this in the future, my email is there, and I'm happy to continue the conversation at any time. So Abby already took my screen away. Perfect. Thank you.
Thank you so much, Karl. That was wonderful. And as Karl mentioned, he was covering a lot of the global aspects of climate change today. We do hope to host a follow-up to this in the future, where we'll cover more of the Maine specific impacts of climate change. So stay tuned for that. Also, if you're looking to take action on climate change right now, Maine is currently in the process of drafting a new climate action plan for our state. It's really exciting. Maine, in our last legislative session, the one preceding this one that got cut off by the pandemic, we passed a suite of some of the most progressive climate legislation in the country and the world, and it's really exciting. And the state is including a lot of people in this process, and we want to help you get involved too. A great opportunity is coming up on June 17th and 18th, a 2-day, very long public meeting from 9 a.m. to 12:30 p.m. both days. I know that's a big ask, but if you can even join for part of it, we would encourage you to do so. My colleague will be sending a registration link through the chat for you to register if you're interested. You can also take action right now by signing our petition to the Climate Council, calling for a strong and equitable climate action plan. All right, let's move into Q&A. Another thing I'm discovering, actually, I can't see the chat. Never mind, I will leave this. No, I can't. I'm gonna stop sharing my screen so that I can see all of your wonderful questions. You've gotten one during your presentation, Karl. I'm just going to scroll up to see now. Peter asks, he has heard that temperature rises at the end of an ice age before CO2 rises. Do you know why that is, Karl?
Well, it's actually when we have had more detailed measurements that have been made from that time period, it turns out that, to the best of our ability, carbon dioxide and temperature rises simultaneously. So there was the thought 10, 15, 20 years ago that the temperature rise led the carbon dioxide rise. But with new data and new techniques, we found out that that isn't the case, that they appear to rise simultaneously. So there are good reasons for that, but the old idea that temperature led CO2 rise is not valid anymore. So.
Rebecca asks, what has caused temperature to rise and ice sheets to melt in our history? And I think she might be referring to the specific last great warming you talked about.
Right. So still an active area of research, but it turns out that the end of ice ages in the past, and I say anywhere over the past 800,000 years and further in time than that, probably has started with changes in the way that the Earth orbits around the sun. So, and there's a whole theory behind that, but essentially the amount of energy that the Earth has gotten from the sun changes through time because the orbit of the Earth around the sun changes slowly through time. So in the past, when of course we were, there wasn't active greenhouse gas being added to the atmosphere by humans, the temperature and carbon dioxide changes prior to that were driven primarily by the changes in the Earth's orbit around the sun, which is ongoing, of course, today, but it happens quite slowly. What we're doing now is adding greenhouse gases at a rate that is, as far as we can tell, unprecedented in Earth's history. So, anytime we talk about these things, rate of change is an important concept. So that last great global warming, again, it's comparable in terms of the carbon dioxide and temperature change that we've experienced over the past century, but it happened over the course of several thousand years. So rate of change is always a big component here. And what we're doing now is changing the system quite rapidly. So.
Christine asks, how is sea level rise measured?
Okay, so sea level rise today is measured primarily in two different ways. One is by tide gauges up and down the coast that are just literally measuring the level of the water through time. And the other way is through satellite measurements. So many satellites have what are known as laser altimeters. So they basically shoot a laser beam down to the surface of the ocean and collect it when it comes back, and they can tell the surface elevation of the ocean from satellite data. So anytime you're looking at sea level rise data, it's usually a combination of those tide gauge and satellite measurements, at least over the past, let's say 100 years when tide gauges really started to become predominant. Now, in the Earth history, I don't want to go down a rabbit hole here, but there's lots of ways to estimate sea level over the course of Earth's history. And again, when you put all that information together in Earth's history, we see that carbon dioxide, temperature, and sea level all go in lockstep together. So they've always, to the best of our knowledge, and over the course of Earth's history, those three have been going hand in hand through time. So.
Karl, this question echoes a couple. Brian asks, how has Maine's microclimate and weather patterns been affected by global climate change?
Well, so one of the ways is, again, it's very, I think about this a lot, is the loss, as I mentioned, through Arctic sea ice. That is having a really interesting impact on actually the distribution of temperature in the atmosphere. So I talked about global average temperature, but when you start to look at things regionally, you see that the regional temperatures are being affected by changes by things like the loss of Arctic sea ice. And it's those change in regional temperatures that then affect our weather patterns, which we're seeing that play out here in Maine. So I wouldn't say microclimates, but regional climates are definitely tied to what's happening on the bigger scale. And some of these impacts, as I said, rising temperatures causes loss of things like sea ice. That then feeds, well, in turn changes the weather patterns even more. So it's all, we call them feedback cycles, and it's an important concept in the climate system. And so we're seeing a lot of those feedback cycles play themselves out.
Oh, it just got bumped down in the chat, sorry. Kate asks, the data for the keeling curve is gathered in the northern hemisphere. Is it still representative of the whole global system, or would that look different if if the data were collected in the southern hemisphere?
Okay, so good question. Yeah, the carbon dioxide data are collected around the globe. So the keeling, the famous keeling curve comes from a station on the top of the Mauna Loa volcano in Hawaii. So it sits at about 14,000 feet in Hawaii. So it samples a really broad sort of swath of the atmosphere. But there are stations in the southern hemisphere which also collect carbon dioxide data at the same time. So we know that we know what the global distribution of carbon dioxide is. And it turns out that carbon dioxide as a greenhouse gas is what we think of as being well mixed in the atmosphere. So you can see from all those data that when carbon dioxide in the northern hemisphere changes, it changes in the southern hemisphere too. So it is at least carbon dioxide is a global component of the atmosphere. So yeah.
This next one is going to be really fun for you to answer. Lake stewards ask us, has there been recent development on the internal structure of glacial sheets causing changing melt dynamics? Do they use something like the GRACE program to pick up on this, or a more analog method? And the reason I said that was fun is because I was lucky enough as an undergrad to get to do research with Karl on a glacier where we were dragging ground penetrating radar machines to map the internal structure of a glacier. Anyways, take it away, Karl.
So sorry, Abby, I didn't hear the beginning of the question.
Oh, sorry. Have there been recent developments on the internal structure of glaciers causing changing melt dynamics?
Okay.
Technical question.
Yeah, I mean, yes, and I heard you follow up and say that you, in fact, were running around glaciers in Alaska collecting those kind of data. Yeah, there's a lot of techniques both where we collect data both on the surface of the glaciers and from satellites to be able to image the internal structure of the glaciers, and particularly the ice sheets as they melt. The internal sort of structure of the glacier is having an impact on the rate at which the ice flows out to the ocean. So I don't want to, well, we could spend a long time talking about this, but the internal structure of the glacier does impact basically how fast the ice is moving from the ice sheet into the ocean. And if we wanted to start talking about climate tipping points and where scientists think that there are particular vulnerabilities in the climate system, glaciers, ice sheets, and the rate at which they flow into the ocean are one of those tipping points. And so we are concerned that as global temperatures continue to rise, the internal structure of the glacier, particularly the ice sheets, is going to have an impact on the rate at which the ice flows into the ocean. In other words, it could start flowing a lot faster into the ocean, which would raise sea level at a much faster rate than it has been over the past couple decades. So it's something that the simple answer is yes, the internal structure of the glacier matters a lot, and we study that in great detail.
Peter asks, what's happening to the jet stream these days? It looks loopy and less dependable. Why?
Yeah. So, right, the jet stream does at times seem to be more loopy, more wavy. I think there's, so I'll say, just in full disclosure, I'm not a meteorologist, but my understanding is that waviness or loopiness in the jet stream, particularly here in the northern hemisphere, is, again, I'll come back to sea ice again. It is thought to be tied to the changes in Arctic sea ice that are happening. So as we continue to lose Arctic sea ice, one thought is that the jet stream is in fact getting wavier. And there are lots of meteorological sort of reasons for that. But yes, people think that the increased loopiness of the jet stream is a function of the loss of Arctic sea ice. It's an active area of research, but it's one to pay attention to because it does seem to be getting loopier. So,
Christine asks, what effects do extensive wildfires, for example, separate things. What effects do extensive wildfires, the Amazon deforestation, and volcanoes have on the climate? And I'll say different effects, but Carl, if you want to go.
Yeah, so I
Specifics.
mean, so there's lots. It depends on what, sort of scale you're talking about. So deforestation on a like a broad scale, like the tropical deforestation they talk about, that is actually that makes a large contribution to the greenhouse gas concentration of the atmosphere. So as you burn large swaths of vegetation, you're actually putting a lot of CO2 into the atmosphere. So that certainly is one large scale impact of large deforestation. Wildfires, again, have different impacts because wildfires tend to put a lot of what we call black carbon into the atmosphere. So soot, basically, black carbon. And that soot, because it's dark, tends to absorb a lot of solar radiation, just like any dark surface that you see. There's a term for this. It's called albedo. And albedo refers to the amount of energy that a surface absorbs. So a dark surface, you all know this, when you walk out on asphalt in the summertime, you burn your feet. Well, it's because it's black and it absorbs a lot of solar energy. So wildfires tend to contribute to that warming because they produce a lot of soot. And one of the compounding reasons why in the Arctic there's a lot of ice melting in the summertime, more so than before, is because wildfires are producing soot, and that soot falls on the surface of a white glacier, making the surface darker. That then absorbs more solar energy, which melts more ice. So again, I mentioned this term feedbacks before. That is another classic example of a feedback in the climate system that we worry about. More wildfires ends up equaling more melting of Greenland and other ice masses in the Arctic. So.
Melting ice masses lead us to our next question. Can you discuss the melting of the West Antarctic ice sheet and what impact it could have on world sea levels?
Great question. In fact, if I had my slides back up, I'd show the slide I had.
You should be able to. If you want.
On this question. Can I? Let's
Yeah.
see. No, do it. Oh, I think can you see that?
Nope.
No? Oh, sorry. Well, anyway, I'll just talk about it. Yes, West Antarctica. The West Antarctic portion of the Antarctic ice sheet has long been thought to be particularly vulnerable to basically increasing temperatures and rising sea level. It's because the West Antarctic ice sheet, actually the rock below the ice sheet sits below the level of below sea level. So in other words, the entire West Antarctic ice sheet may be particularly vulnerable to increasing sea level, which would cause the whole thing to become unstable and basically melt and go into the ocean at a really increased rate. So this has been something we've been thinking about for a long time. And in fact, it goes back to one of the first people to think about it was a glacier scientist named Terry Hughes, who was at the University of Maine for a long time. And so West Antarctica there it is. Now can you see that?
I was hoping that's the one
you
wanted.
You pulled it up. Yeah, exactly.
I pulled it up.
So good job. Yeah, so you can see in this figure, you'll see that. Okay, so here's Antarctica. The color bar is the amount of ice lost between 2002 and 2017. And you can see that West Antarctica is red, particularly in a region where that little box is. There are two large glaciers there. One is called the Thwaites Glacier, and one is called the Pine Island Bay Glacier. And those two, and we have colleagues of mine from here at the University of Maine have been going down to that area for the past several years, doing lots of different work on these glaciers. So this is the point, though. That part of Antarctica, that part of West Antarctica seems to be losing ice at a much faster rate than the rest of the Antarctic ice sheet. And it's due to the way that just the configuration of West Antarctica, the way that the bedrock is below sea level, and the way that the ocean interacts with the glaciers in that part of Antarctica. All of that is combining to make that particular part of West Antarctica seem to be particularly susceptible to melting and increased ice flow into the ocean. So we were watching and actively studying this because this is another example of one of these climate tipping points. If melting and ice loss from West Antarctica increases significantly over the coming decades, that would have a much bigger impact on sea level rise than we've seen over the past several decades. So when we talk about tipping points in the climate system, West Antarctica is definitely one that we are particularly aware of.
Right, there are a lot of other great questions in the chat, but unfortunately we're just about out of time. And I wanted to leave a minute to tell you all about next week's Lunch and Learn, which is also very exciting. We are going to be joined by Maine Secretary of State Matthew Dunlap, as well as Lewiston City Clerk Kathy Montejo, and they will both discuss everything that you need to know about Maine's July 14th primary and voting in Maine during the COVID-19 pandemic. If you don't currently receive our emails with invites, you can sign up on our webpage, maineconservation.org, and we'll try and do some follow-up with you all on the questions that we didn't have time for. Thank you all so much for joining us on this beautiful Friday. I hope you can get out there and enjoy the weather. And Karl, thank you so much. That was great.
Okay, thank you.
All right, take care, everyone. Bye-bye.